So we're gonna get started. Good morning. Are you still having fun? I heard it's pretty intense now with all the coding and stuff like that. But hang in there. What is BWSI? So lame. Come on, louder. Louder. Okay, that's fine. So today, the CubeSat class is on a field trip, so they're not here, and then so is the remote sensing teams. But we do have our middle school classmates. Say hello, right? Yeah. And I would also like to welcome our students from Nauset Regional High School, Warrior Works. So raise your hand. So they're running a shadow program, and they will be here for the final competition. They're working on their own race car, so they will be racing in the final event. So be nice to them. All right, so we'll get started. How many of you remember what happened about 50 years ago? Great. How many of you want to go to space? All right. So today is your lucky day yet again. We have, it is my pleasure to introduce Professor Kerri Cahoy from MIT's Aero Department. Also, she was responsible for starting the CubeSat program class last year. So with that, let's welcome Professor Cahoy.
All right, thanks everyone. I'm Kerri Cahoy. I'm a professor in the Aeronautics and Astronautics department here at MIT. I run a lab called STAR Lab, Space, Telecommunications, Astronomy, and Radiation Lab. And it's about 30 graduate students big. My background's in electrical engineering, and my lab builds shoebox-sized satellites called CubeSats. We've launched 3. We have 1 more going up this fall. We're building 3 more for NASA. We're part of a constellation with MIT Lincoln that's sending 6 more in about 2020. And another collaboration with MIT Haystack, they're sending another 2 also in 2020, so it's getting a little busy. But I wanted to talk about space exploration and how we can make it possible to learn about the hard things about space exploration from middle school, high school, all the way through college and graduate school, and kind of just educate you about kind of a little bit more about space exploration, why it's hard, why it's worth doing, and how we can start working on some of these hard problems using balloons and CubeSats as kind of first steps. How many people here have worked with model rockets before? Okay. How many people have worked with a weather balloon before? Okay. How many people have worked with a CubeSat before, know what one is? Couple. Okay, so just want to make sure I calibrate properly. Please ask questions. I'm happy to take questions. I will try to scan for hands and try to uniformly pick across the room and not just pick from one area. Anyway, so this is kind of an overview, so I'll talk a little bit about why we even want to go to space, what makes it hard, what's a weather balloon, and how can it teach us how to overcome some of the hard things about space exploration, what's a CubeSat, and how does that help us, and then I'll wrap up with a summary and some ponderings on the mythical nature of the space business. So why space exploration? Why number 1 is get above the atmosphere. So I have a picture here. And this picture is showing, does anybody know what it is? So this is the opacity, what can get through the atmosphere in terms of percent, and this is wavelength. So this is like radio waves over here. These are like X-rays and gamma rays down here. And this is the rainbow here is where visible light is. And so this is basically the air between the surface of the Earth and space blocks short waves, gamma rays, X-rays, ultraviolet. To some extent, we still get sunburn. And then it lets through visible light and some near-infrared radiation. And then it blocks a whole bunch more, lets through radio waves, and then, again, blocks long wavelength light. So basically, everything we ever do with telescopes and radio telescopes on the surface of the Earth is really only in these small pieces. Those are the only parts of the universe that we can explore from the ground and understand. So in order to be able to understand what's going on in terms of the creation of the universe, the evolution of stars, planets, and systems, whether or not there's life out there, any signals and information that may be contained in wavelengths other than these little windows, we don't really know that well. And it's really even hard here because of radio frequency interference, because of all the fun stuff we've got going on down here on the surface with wireless and Wi-Fi, radio waves, and data. And here we get, there's weather and clouds that make it a little bit difficult to be able to see far out. So we want to go to space because it's like trying to explore with shades down a lot of the time from the surface of the Earth. The other thing is, this is a picture of the Earth from Apollo 17 in 1972. It's called the blue marble image of the Earth. We want to be able to see the Earth as a whole from a distance and really take advantage of understanding our planet. We can do things like look at weather, storms, and more importantly, defense. So an image like this is what you would want if you were looking for early missile warning and defense systems. So for defense purposes, for science purposes, and also for communication, if you wanted to be able to send data to the entire planet all at once, the only way to do that is to send data up to a satellite and then create a spot beam that covers large fractions of the Earth and send it back down. That's how you all get cable TV. I know you think it goes to your house, but really it goes up to a satellite and then down to a radio dish that's called a head end, and then it's distributed back to cable to your house. So this is how we get programming on a regular basis. So that's one reason we go to space. Another is to find out what other solar system objects are like. This is Mars. This is a 360-degree panorama from the Mars Curiosity rover at the Vera Rubin Ridge. We can send robots, like the race cars you're building and the things that you're learning to do with build and remote operation and autonomous navigation. We're sending them to other planets in our solar system to find out what it's like, to see if there ever was possibly life there, were they ever habitable, if they were different in earlier times than they are now, what happened? Mars used to have a very active magnetic field. It does not anymore. It just has crustal remnants. Did that have to do with the existence of a thicker atmosphere and water on the surface? We're trying really hard to find out. There's a lot of, well, it can be kind of funny, a lot of articles lately about methane possibly being detected on Mars and kind of jokes as to where that might have come from. But it's an open question, what is going on planets in our solar system. So going to space and launching these vehicles is one way to find out. NASA just selected a mission called Dragonfly that's going to send a UAV to Titan, which is one of the moons of Saturn. More methane. But it's exciting. So these are exciting missions that we can learn to be a part of. And some of these missions are long. So they're going to count on people like you, and it's going to be you guys when they're landing and exploring who are the people who are operating it. So training you guys now is a good idea. We can get samples and sometimes even bring them back. This looks like a lump of coal, but that is a spacecraft. That spacecraft chased a comet, stuck out a little aerogel capture screen, grabbed particles from the comet, closed itself back up, came back to Earth, and re-entered at screaming speeds. It went from Mach 36 to subsonic in under about 2 minutes. Hit about 2,900 degrees Celsius, 30-ish Gs of deceleration, landed on the surface intact with its samples. So humanity is kind of awesome. Scientists are nuts. We decided we're going to go chase down a comet, take a swipe of its tail, and bring it back and study it. Why did we do that? Well, this particular comet used to be a comet that was out kind of in the Kuiper belt by Pluto. And then it had a gravitational encounter with Jupiter, and its orbit changed. And now it's an orbit that is kind of at almost a Earth distance from the sun. And so we wanted to see what it was like, because its orbit got perturbed, it got knocked inward, and people wanted to go take a whiff of that comet and bring it back and analyze it in this aerogel. Early warning for solar storms. This is a diagram of the sun and the Earth and the moon going around the Earth. And these points, does anybody know what these points are up there? These are Lagrange points. So these are points where the gravitational pull between the sun and the Earth is just about balanced, so that if you had a test particle and you put it here, if it were a little closer to the sun, it would go into orbit about the sun. If it were a little closer to the Earth, it would go into orbit about the Earth. But if it's at this point right here, it kind of hangs out and stays. So these are Lagrange points, kind of points of balance between the sun and the Earth. So there's one on the sun side along this line called L1. There's one on the far side, so in the shadow of the sun, called L2. This is a great place for really good astronomy telescopes, because it's behind the shadow of the Earth from the sun, so it's nice and dark and unperturbed. So they like to put big astrophysics and astronomy telescopes out at L2. Over at L3, which we don't normally put things there, does anybody know why? It's really far, that's one reason. That's right, the sun is in the way. So sending radio signals or any type of signal back to the Earth from that point is kind of hard. You need a relay. This L4 and L5 point are called Trojan points. Trojan points are places where we have asteroids building up in the Jupiter system, so there's the asteroid belt. And so you have debris and rocks and all sorts of stuff piling up at these. These are stable Lagrange points, and these are unstable. So things don't tend to pile up at L1, L2, L3, but they do at the Trojan points, L4 and L5. So if we were worried about the sun, which is this big, angry fireball that's constantly spewing ionized particles at us in the solar wind at very high speeds, and we're only protected by what? Does anybody know? I hear muttering. Our atmosphere helps a little bit. What else? Our magnetic field. So Earth is like a magnet. It has a liquid iron core, and it has a dipole field. And the Earth's magnetic field protects us from the ionized particles coming in from the sun towards us. So if we wanted to get a better prediction, and the system's kind of going this way, we would send a spacecraft to L5. It would see anything being ejected from the sun, a coronal mass ejection or something, in advance, and could warn Earth in advance. Right now, we don't really have that. So wouldn't that be smart to do? Yes. So that's another good reason to go to space. And then there's also human exploration. And this week's a good week to honor man on the moon. Buzz Aldrin is shown here on July 20th, 1969, which is going to be 50 years this Friday. And I am saving my Saturn V rocket Apollo moon dress to wear on that day. But it's really important for humans to get out there, reach out there, and touch the moon, Mars, and explore. So really push our boundaries. We're an exploring race, and that's what we've done here on Earth, and we'll continue to do through the solar system. This is Starman. So this is the most we've done recently. So this is Elon Musk's Tesla. That he, if you're not aware of this, Elon Musk launched his own Tesla car as a test payload on the Falcon Heavy first launch, and he put it into orbit about the sun with a dummy in it. So we have Starman, who's currently in heliocentric orbit about the sun and has its own tracking number. That was last year. So what makes space exploration hard? What are the hard things? What are the things that are the challenges that we need to work on? So here's a long list. I'm going to go through them one at a time. But basically, surviving a rocket launch, operating really far away, you're moving really fast, you're in a vacuum, so there's no air, you go through really cold and hot cycles, you have really limited power, you have to deal with radiation and atomic oxygen corrosion, you have ionizing radiation, you can get hit by micrometeoroids, and also there's a ton of paperwork. So one at a time here, all the things. So this is a Falcon Heavy launch of CubeSat 6. Surviving a rocket launch is no small task. Has anybody been to a launch?
No, 30 seconds.
Okay, you feel this giant pressure wave from 2 miles away hit you. It's like a strong, hot wind just blow into you. Those rockets are loud and they shake for a couple minutes. And whatever you build had better not fall apart when it is shaking that hard and vibrating that much.
9, 8.
So just
7,
to give you a sense,
6,
it's
5,
very loud.
4,
It's very,
2,
very high vibration environment.
ignition.
And also you have this pressure gradient going from air pressure at sea level to vacuum really quickly. So this surviving that moment is really quite difficult. You have to do things like make sure you glue down your electronics. It's called staking. You have to make sure that you vibration test everything and make sure it's not going to shake and break off in advance. There are a lot of different things that we have to take care of to make sure that we can survive a launch like this and have whatever is at the top of that rocket survive.
Under the power of 5.1 million pounds of thrust, Falcon
Yeah,
Heavy
that's a lot
is
of
headed
thrust.
to space.
So
With throttling
I'm
down
going to
at
skip
2 +
because
40 seconds
if you haven't seen one of these before, the Falcon Heavy booster landings are quite remarkable and a real accomplishment. I've had students working at SpaceX. So basically, those side boosters on the launch, in order to bring launch costs down, does anybody know how much it costs to launch a rocket? A lot. About $100 to $150 million regularly.
Side boosters landing burn will
So
begin
that's
as well.
a lot of money. And here we have the boosters coming down. There are 2 of them. They're going to land on launch pads. This upper right picture shows them coming down. And this one's a nice one too. So designing the control systems and figuring out just how much fuel, extra fuel you have to be able to bring them down instead of let them burn up in the atmosphere is really a lot of work and really impressive. So these control systems, keeping them upright and carefully landing them and getting back to target are really, really impressive. But it should reduce the cost of launch and make space more like air travel where you can reuse the same plane to go across the country. It'd be really silly if we used a plane once and then threw it away. So, all right, so you're really, really far away in space. What does that mean for operations? It means you kind of need a powerful transmitter and receiving dish to be able to talk to your spacecraft or your rover, and you may not be able to access it all the time. So using these things are expensive. This is the Goldstone Deep Space Network dish. It's a 70-meter diameter dish in California. Just yesterday, I was up at Westford, Massachusetts, where we have an 18-meter dish at one of the MIT Haystack and MIT Lincoln sites. You need big antennas or possibly laser comm systems, which is something that I work on, to be able to talk to your spacecraft. And this is hard. These are expensive. You have to make sure that you know what you're doing with your commands. Anybody here play football? Or has played football? Or do we get none of the athletes? We might not have gotten athletes. But if you've ever heard of a playbook, you have to have kind of like a playbook for your spacecraft and for your mission, where you know what you're running in advance, you practiced it on your engineering model in the lab, and you do that command sequence and you hope it works out. And then you have to try to figure out what went wrong. And you have to use assets like this and have just a little bit of time on it, because using this is also expensive. So that also makes space hard. You're moving really fast. So this is just an example of satellites moving quickly. And I wanted to show you Elon Musk's Starlink satellites, which were very reflective and specular, moving across the Big Dipper and Little Dipper. Can you guys see these dots here? Yep, so this is the Big Dipper, this is the Little Dipper. These are a train of 60 Starlink satellites that Elon Musk put up. And my point here is that depending on where your satellites are, you can't just have your big dish pointed up and then expect to talk to your satellite or your rover or your mission. You may have to slew the whole thing and track to be able to point at these as they're moving across the sky. It only takes, for something that's where the space station is in low Earth orbit, it only takes 10 minutes for the thing to go from horizon to horizon. And so you have to have a system that can point and slew quickly, and it doesn't go on the same track every time. It can't just go back and forth and you build like one track and like a roller coaster and goes back and forth. No, because sometimes it's over there, sometimes it's over there. Depending on the orbit, it changes where it is. And so these tracking systems are kind of a pain, and they're moving pretty fast. And so that's a challenge too. That's kind of hard. The other thing about moving fast is if you want it to move any more than just its orbital velocity, if you want to be able to enable motion on your satellite and keep it from tumbling and have it pointing in any one direction, you have to use actuators like thrusters or reaction wheels to be able to keep it oriented in the way that you want. It's possible to mess that up. It's possible to get your wheels spun up too fast, to get your satellite spinning so fast that it spontaneously disassembles on orbit. This has happened. It's possible to have your thrusters doing the wrong thing. It's possible to have your batteries explode on orbit. So all of these things are difficult. But having chemical propulsion systems, hydrazine is one of the fuels that's used on spacecraft. Does anybody want to guess how difficult it is to get hold of hydrazine? Super difficult. They make you basically keep it in a bunker. You have to have all sorts of licenses. You have to have all sorts of permits to transport it around. This isn't easy. Electric propulsion is a little easier, where you can have like ionic fluids and salts and things that you can use, and maybe just use xenon and high voltage. But then you have high voltage. Does anybody know how much trouble you get into when you want to run something high voltage in a lab? A lot of trouble. So these are hard things. And then you have a lot of data and sensor data. So how many people really love geometry? Okay, good. Keep that up. How many people know what a coordinate transform is? Okay. Okay, so there are all sorts of different reference frames and coordinate transforms that you have to take care of when you're using sensors on satellites. You have to map where the sensors are to the correct frame and use all that data to figure out where your satellite is currently pointing, where your sensors, and basically put all that sensor data together, and then figure out what you wanted to command your thruster to do, or your wheels, how much you wanted your wheels to spin to get your satellite to move somewhere else. And pro tip, so you can't translate anywhere without a thruster in space. And it takes a lot of energy to go from one orbit plane to the other, actually. It takes less energy to go different places along the same orbit, but moving orbit planes takes a lot of energy. And then there are wheels and things to tip and tilt your satellite. And we use the Earth's magnetic field, so we can use the fact that there's a magnetic field there, and we can pass current through a coil of wire and use that to generate a torque to tip and turn ourselves. So there's lots of different things. So these are reaction wheels. This is a thruster. This is a Hall effect thruster. These are magnetorquers. So these are coils of copper wire that are wound that we pass current through, and they generate a torque when they're at different orientations with respect to the Earth's magnetic field in orbit, if you're close enough to the Earth. If you get far from the Earth, then the field strength weakens as what? Does anybody know the relationship? R squared, yeah. So these are all things that are important. You're in vacuum. So vacuum is a problem. Does anybody know why vacuum is a problem? Yeah, there's no air. So if you're hot and you want to turn on the fans, like everybody's computer has a fan in it, right? Everybody knows what these are. You probably scavenged them and like hooked them up to things. So fans don't work. Fans don't work in vacuum. There's no convection. You have to touch something. You have to reach out and touch something to cool down, right? You have to radiate, so you have to conduct heat a different way. And that can be very challenging. The other problem is when you're in vacuum, if you had a part that was kind of sealed, and it went up in that rocket from the surface to space, bam! It would explode, depending on how big it is and how strong that component is. That's a big problem. So you have to make sure that you don't have things that are sealed that shouldn't be, that you can outgas properly. There's also this thing called cold welding. So metals don't know when there's no air in between them when you're in a vacuum. When they touch each other, they don't know that they're different pieces of metal. The electrons and the protons just kind of work together and will literally weld. So any metals that touch each other in the vacuum of space will literally do something called cold welding. They will stick together like they are welded together, like that movie just showed. So you can see cold weld happening right here. So these are two different things, and that's a cold weld happening microscopically. This happens. So there's a Galileo spacecraft. It had this beautiful big umbrella high-gain antenna. It was supposed to deploy into a giant dish and send data back to the Earth. It was made of metal. It got cold welded stuck and never deployed. That's right there. That's a big bummer. Space is hard. All right? They had to use really terrible little low-gain antennas to get data back and try to rescue what they could of the mission without high data rates. Jupiter's far away. Yeah. You can use coatings, different coatings to help with that, to keep the metal from being metal on metal. So you would treat the surface. And we'll talk a little bit more about that in a second. So yeah, exactly. And then there's outgassing. So anything that touches the surface and is absorbed or is adsorbed, which is an adhesion to the surface, will outgas when it gets into a vacuum. So if it was like deposited into your system on the ground and your lab wasn't very clean, and then you go up to space, all these particles and all this glop kind of evaporates off of your parts, and it can land, let's say you have a beautiful mirror or a beautiful lens. All this gunk can like come off and then just deposit onto your lens and make it all dirty. Or deposit onto your electronics and make them not work. It's fabulous. Lots of problems. So this is one of the reasons why we try to make sure things that go into space are so clean. All right. Cold and hot. It is worse than some weather patterns. So basically what we have here is the Earth. The Earth's here, the sun. We have the eclipse. And imagine that what's labeled here is the moon's orbit. This could be any satellite orbit. And you have the Earth's shadow that you're going into and then coming out of. When you're in sun, this is at the orbit of the Earth, 1360 watts per meter squared coming at you. And when you're back here, there is none of that, and you're really cold. So you have cycles of really hot and cold, and every time you go around, if you're at the same height as the space station, you're doing this every 90 minutes. That's a lot of times. You're cycling hot and you're cycling cold, and you have to make sure that everything works. One way that balloons are useful for testing this is when you're testing a high altitude balloon. This is kind of the temperature here, and this is degrees Fahrenheit on the bottom and degrees Celsius here. So this is about 60 degrees Fahrenheit at the surface. When we've sent up weather balloons, which I'll show some pictures of, we get to about 30 kilometers altitude, about 100,000 feet. And you go through this huge temperature gradient. It gets really cold here. And then it flips around, and you have a couple of different inversions. And up here, this is like temperature, but you don't have enough particles there for it to like be the same as temperature on the surface. So this is just kind of like particle kinetic energy, but it's not really thermal. It's not the same as a temperature on the surface. There's not enough gas for it to be as effective. But you can use a balloon to test how well your hardware works, going from nominal temperatures to something very cold. And this is some data from an on-orbit spacecraft where you can kind of see. So this is temperature in degrees Celsius. This is inside the satellite. This is outside the satellite. and this is minus 40 C to plus 30 C, and this is time in seconds. And you can see getting hot and cold, hot and cold, hot and cold as it's going into and out of eclipse. And you can see this is inside the satellite, and the outside it's even bigger swings. More importantly, you can also see the battery charge here. So you can see what I'm going to talk about in a second, which is power. That you have lots of power when you're in the sun, and then you have no power, and you have to run off of batteries when you're in eclipse. Unless you have some type of nuclear power, but those are very politically contentious and only used for deep space exploration when needed. All right, this is how we test hot and cold on the ground in the lab. This is a thermal vacuum chamber. This is a satellite in a thermal vacuum chamber. These are giant cylinders that we pump all of the air out of, and we use liquid nitrogen and sometimes liquid helium if we needed to get really cold. Liquid nitrogen is how cold? 70 Kelvin? Do I hear some answers around 70 Kelvin? It's pretty cold, right? What's liquid helium? Does anybody know? It's about 4 Kelvin. That's right. So depending on how cold you need it to be, you'll have lots of pipes and tubes going into this thing, piping cold gases in to make it cold just like space. And then you'd have heaters in here that would heat it up just like space. And these chambers basically have to be as big as the thing that you wanted to test for space operation. So there's some very big ones. We have a small one in my lab. And so this is Sentinel-2A satellite. There are power limitations. So this is a video of a solar panel test at Lockheed Martin, and I just wanted to show. So these things are huge. Can you see these people down here?
That the 16 restraint mechanisms
so these are folded up deployables
6 sets of
on
hinges fully
geostationary
locked into
spacecraft
place.
that are just enormous
Once the
to
wing
generate
is fully
power.
deployed, the spacecraft
So not
can
only
receive
do you
full
have to
power
have
from the
these
sun
giant solar
and
panels
the 2 solar weather sensing instruments
to generate
solar
power for your
ultraviolet
satellite,
emitter, and the extreme
you also,
ultraviolet
and they
X-ray
like to be,
radiance sensors
they
can
like to be
become
cold.
operational.
You also have
The
to
successful
have
ground
giant battery packs, just huge banks of batteries. These are the batteries for the Hubble Space Telescope that the solar panels have to charge up so that you can use them to keep everything alive and running when you're in eclipse, when you don't have enough power. Managing batteries is a real challenge, and batteries like to stay warm, ironically, so you have to use your batteries to keep themselves warm. And if something bad happens and your batteries get really cold, you can lose your whole mission. It's kind of sad. So those are hard things. There are lots of sad things about space exploration. All right, so ultraviolet radiation. So the same thing that makes you tan also tans stuff in orbit. It will make your glass, like your window or your lens, go from clear to kind of Coca-Cola colored. It's really fabulous. Any polymers or glass. It makes plastics brittle, structures brittle, more easily breakable. And then also at, for low Earth orbit altitudes, I may have lost my laser pointer, there we go. We have atomic oxygen. So this is not molecular oxygen like down here, but atomic oxygen up near the surface, and it corrodes metals rapidly. So this is a picture of Eureka silver corrosion that was recovered and shown. So this is just what corrosion does to metals on orbit. So you have to passivate all of your metals that go to orbit. It's called anodizing or allodyning. You basically put them in a bath and you turn them into an anode and you pass a high voltage through them and you kind of create this protective coating on them to keep atomic oxygen from corroding your satellite in orbit. You also have ionizing radiation. So we mentioned the sun looks so friendly up there. It's actually a really angry giant fireball that's spewing hot ionized gas at us all the time. It spirals out from it. We're protected by our magnetic field, like I mentioned before, so you can see the Earth's magnetic field line. This is the solar wind. It actually blows the Earth's magnetic field way back into a magnetotail here, all the way far back over here. So we have satellites that are orbiting in here, and all of these ionized particles see these magnetic field lines and actually get trapped around them, and they spiral around them. And so there are belts around the Earth where we have ionized particles that are trapped around field lines. What are ionized particles and why are they bad? Well, yep, up there. can cause charging. They can deposit on the satellite and cause charging and arc discharges. More importantly, they really mess with your electronics. So you guys program electronics, right? You like sending commands and putting things in memory and thinking that those ones and zeros that you're putting in memory are staying ones and zeros. Surprise, in space they don't. When ionized particles hit your electronics, they can change the state of just about anything. And so you have to design systems that can power themselves down and back up again, that can look for errors and correct them and have error correcting codes, and try to design shielding so that the particles have less of an effect. So these are all sorts of different levels. These are cosmic rays. Those are from when stars go supernova. They can come from anywhere, not from our sun. Those can come from any direction all the time, and they also affect electronics here on Earth every so often. They get all the way down through the atmosphere. Then there's, from our sun, solar flare and radiation belt particles. These are the discharges, and you can have all sorts of problems caused by ionizing radiation. So we have to try to design electronics that can survive that and are shielded from that, and be prepared to have our satellites reset spontaneously in the middle of whatever they're doing. Fun. Surprise. Yeah. And then there's micrometeoroids. If that weren't bad enough, they're actually like little things that are just kind of flying through space and can hit you, just like the video games. Yeah. So there are people who, instead of going searching for gold, like in the gold rush, there are people who go to Antarctica and melt snow. And they melt snow and they find things like these micrometeorites that are found in Antarctic snow. So this is an example of what a micrometeorite looks like. This is about 100 microns across. This is an electron micrograph image of a hole that was made in a panel of a satellite called SolarMax. Wait a minute. How do you get a picture of a hole on a satellite? Yeah. Yeah, in this case, there's a hint right here. This is back when the space shuttle was working. So the space shuttle used to go up and service satellites. It would grab satellites, and the astronauts would fix them. That's what it was doing. It was very convenient. We still haven't figured out a way to do that with robots effectively yet. We're working on it. This particular example is kind of a funny story because normally the satellite has some type of spin, and they were trying to grab this satellite to fix it. And they it had a gasket sticking out somewhere it shouldn't have been, so they couldn't grab it with the arm that they were planning on. So they're like, oh, it's not a problem. It's spinning. We'll just have the astronaut stick his hand up and grab the panel and then stabilize it, and they'll fire something to try to cancel the spinning. And that worked terrible. They almost lost the satellite. It ended up spinning up super fast. It was almost one of those spontaneous disassemblies of spinning things. Ground control managed to get the satellite back under control just in time, and then they spun it down and then had the astronaut grab it, which is took longer, but a much safer way to do things. But that's a funny story about that. So anyway, so this came from a satellite that was taken in on the space shuttle. Also, licenses. If all of that weren't hard enough, there's also stacks of soul-sucking, mind-numbing paperwork that just makes everybody's lives miserable. So if I haven't motivated you to get over all of these hurdles for space exploration for all those awesome reasons that I talked about at the beginning, there's one more thing. There's a lot of really, really boring paperwork and regulations and things that you have to get around, and you get in a lot of trouble if you break the rules. So you have to have licenses to operate your radio. You have to have licenses to take pictures with certain types of cameras and certain resolutions. You have to prove that your satellite isn't going to stay up there forever and be a piece of junk in space. You have to prove that it's going to come down and burn up in the atmosphere in the right amount of time. Lots of paperwork. All right, so how can we start attacking some of these problems and training ourselves to handle them so that in a few years, we can be the ones who are operating these rover exploration missions, these manned Mars missions? What are the things we can do now that teach us how to handle some of these hard things? So weather balloons are a great way to do this. I showed that profile of the Earth's atmosphere going up and where weather balloons are with respect to space. So a weather balloon is just a latex balloon with helium, and you can also use hydrogen. that is lighter than air to go up. For those of you who have worked on model rockets, there are a lot of analogs to that. You have your balloon, you have a parachute, you have a radio system and a tracking system, and then you have your payload boxes. They're roughly about 6 pounds each. And it's not too difficult to be able to do this. You can call your local FAA office and let them know that you're putting one up if you follow the rules. There's no really special licenses or paperwork you have to fill out. You just kind of have to let them know and get their okay for wherever you're going to launch it from. So this is Paula. She's in my lab. And we are filling a 1,600-gram weather balloon with helium from those helium tanks. So weather balloons teach us, they don't teach us about some of the things, like rocket launches, but they are far away. They do move fast. They are up in vacuum. They do get cold and hot. You don't have a lot of power. And you don't have to deal with a lot of the paperwork and the radiation, but you do have to deal with a lot of these things. For some people, you'll look at that list and be like, that's still pretty hard. Is there an easier way that we can take a baby step first before we do the weather balloons? And yeah, so you can. I brought an example here of just a little CubeSat structure with XB radio. And you can do a tethered balloon really easily without a permit, without calling the FAA. You just need some kite string and some helium and maybe a 100 or 200-gram weather balloon. And you can tie it to this CubeSat, and you can send it up at least 150 feet without any permits at all, as long as you're not too close to an airport, right? And so you can go up, even up to 500 feet if you let the FAA know about a day in advance. So you can do this pretty much anywhere, any school field. We've done it here on the MIT football fields. And this is a great way to get started. So you miss some of the harder parts, but you get the far away and moving, and you get the power limitations, and you get the remote operation. So this is a great, easy way to start. So if you've never done this before and you'd like to, and you have a wireless radio that you can use, or even if you just want to send a GoPro up and take some pictures, this is a great way to do it. I can send a GoPro up, again, with a 100-gram weather balloon and probably one of those little party helium tanks. And it's fun. So that's a great way to be able to learn about some of the hard things in space. And we've done this for class. So this is the MIT football field. This is a 100-gram weather balloon. That's this guy over here. And it's just on a tether. And we can collect data and learn things about attitude control and imaging just using a tethered balloon. The only things you really need, stuff that you probably have at home. Maybe not the fishing scale, but you can get those on Amazon for 10 bucks. And the helium. Most grocery stores even have helium. So high-altitude weather balloons are much more fun. So they get really all the way up to space. So this is one that we launched from Coxsackie, New York, which is about 3 hours from here. Went up to 106,000 feet, and then it came down in Rutland, Massachusetts. So if you're going to do a weather balloon, it's like planning a small hiking trip. So you get up there and you launch it, and then you have a navigator and yourself chasing that thing all the way back to where it lands. It can land anywhere. Try to use some of the forecasting tools that they have online to figure out where it's going to land based on the weather and wind patterns in advance so that you're landing in a dry area. Yep. Right. So here, it's kind of got the jet stream pushing it along, and then it finally gets above it. Once it's above it, it just goes straight up. And then it pops, because eventually the pressure of the helium that was in the balloon, because the external pressure is decreasing so significantly, it gets to the point where it's so much that the latex balloon just pops. And then it comes back down, pretty much straight down, and then the jet stream picks it up again with the parachute and takes it down to where it's landing. So it can land anywhere, so it's kind of a fun hike. So bring all your hiking gear and some power bars and water or something when you're going to try to find that thing, and wear blaze orange. So here's kind of a list of things that everything you could possibly need for a high altitude balloon flight. I will say that lots of zip ties are a good idea. A large bucket to pretend is your payload is also a good idea, because trying to figure out how much lift the balloon has on a scale or something else doesn't work so well. Also, those things, like if it's really windy, you'll need like 10 people to try to keep it from blowing down and over. It's kind of fun. And pool noodles are good to put on them because they might land somewhere wet, and then at least you'll get to see where they landed. So these are all fun things. These are T-tanks of helium in my mom SUV. They clank and make a lot of noise if you don't put some padding. But you can fit them in a car and drive them wherever you need to. And this is a picture of our balloon bursting. That's kind of the parachute, and you can see the little pieces of balloon, and that's the Earth down there from space. So this is really fun to be able to do. Things that you can fly in the payload boxes. You basically just have styrofoam boxes, and you want to test them in advance by throwing them in the freezer. You don't really have to put them in the oven for this because it gets colder, not hotter, as you go up. So you can get a roughing pump on Amazon for tens of dollars that'll pump down your electronics. You can see how well they work in vacuum, how hot they get. Or you can just run the whole thing in its payload box, stick it in a freezer, make sure it still works. That's a good test. So you need things like your computer and your camera, some kind of tracker, lots of batteries. So lithium-ion batteries are a good idea. SD cards to save your data, antennas for your radio and tracking system, as many sensors as you feel like putting on it, and then also try to make sure that it is kind of protected from humidity and moisture because you might go through a cloud on the way up or something. So you don't really have control of that. So here's some pretty pictures from a high-altitude balloon test. And then the things that you want to bring for your recovery, so you want to plan for a hike, like literally dress for a hike, wear blaze orange in case you end up somewhere where people might be hunting, just to be safe. People can find you. Have a compass, have sunblock, have bug spray, maybe think about bringing a portable kayak, depending on where it might land. But these can be fun outings to do as a club or as a group. And again, they're not really hard. It's an easy thing to do on a weekend. One of the important things is having like one of those like BB gun pellets with like nylon fishing wire, or even a small fishing bait, something that's heavy, and then that has a fishing wire or a nylon cord on it that you can slingshot up through your payloads and pull back down, because odds are very high that your balloon comes down in trees. Almost always comes down in trees. Trees kind of stop things. So this is the parachute, and these are our payload boxes. So you kind of want something that you can shoot up and over it and pull it down. And so we got it back down. And this is my class that we took out to do this, and these are the payload boxes. These little straw things here are the antennas for their tracker. And they have a bunch of cameras and all sorts of things cut out the sides of the styrofoam boxes. You can just get like one of those styrofoam coolers from Walmart or something and use that as the payload box. So anyway, really quickly on CubeSats. So CubeSats are another way. So once you've graduated from the tethered balloon and the weather balloon, there's also a tiny satellite that is pretty easy to get to space. So CubeSats were invented in 1999 by a couple of professors in California, Jordi Puigdemont and Bob Twiggs. And a standardized CubeSat is essentially this size. And I can pass this around if you guys want to see it, or you can come up and touch it if you want. It's totally fine. So it's about a 10 by 10 by 10 centimeter cube, and you can stack 3 of them. The idea here was, remember how much rockets were? How much were rockets? How much do rockets cost? $150 million, right? And then you've got, in addition to that $150 million rocket, you have a satellite that's this big. Do anybody have an idea of how much these satellites usually cost? Yeah, $300 to $500 million. That's a lot of money in one place. So the hard part is, how in the heck do you convince somebody to let you put your little test box on their precious rocket with their precious satellite? Anybody have any ideas how you do that? Yeah, in this case, you put it in a box. And essentially, you put it in a spring-loaded box, just like a jack-in-the-box. So the novel contribution here that made this all happen is they're like, hey, I'm just going to put my little test satellite in this safe box. It's a safe box. It closes. It doesn't open until everything's on orbit, and you guys' big mission is out of the way. And then the spring will open, the door will open, the spring will push it out, and we'll have access to space. So these guys went through a stack of paperwork, and they made this work. And you know why it works is because these rockets, they're $150 million rockets, but they're really big. You saw how big that thing was, right? They have to get that precious $300, $500 million satellite just to the perfect orbit. And to do that, they have to have extra fuel and have to be designed to have extra fuel because on the day of the launch, the weather conditions might be different, right? So they're not going to necessarily need all that fuel. They have tens of kilograms on their rocket that they end up putting just dead weight, just ballast, like on a boat. Seriously, they just literally put bricks. And so these guys are like, well, instead of putting bricks, how about you put our little boxes? They're safe, they won't hurt your satellite, and then we can get up to space. So that's what happened, and that's how that all worked out. So these are CubeSats. This is a Peapod deployer. It's just a little spring-loaded jack-in-the-box box that goes on the rocket. So this is a bunch of CubeSats. The satellite's underneath it. This is a ring on the fairing. The top of a rocket's called a fairing, that nose cone area. And they're just bolted in their little jack-in-the-box deployers, almost for free. And you're able to get these tiny little systems up to space. And this is history being made. So after a few years of this, people really started to get the hang of it, and they started intentionally designing systems that were super capable, that could fit in this form factor, in these little one-use cubes or 3U cubes, that could do amazing things because you could get up to space so effectively and easily. So this is a Indian PSLV, and it had 88 of these on board, this whole stack from a company called Planet Labs. And so this is just its camera showing it just shooting these things out. So this really, really changed the way space is done. And now everybody, pretty much any high school, any college, can propose to NASA to launch one of these for free. And all you have to do is build your satellite. And it can go up there. So every November, there's a proposal call, and you can submit a proposal to put a satellite on orbit, just like this. It's great to have a lot of satellites on orbit because there are big satellites that are really far away. This is a geostationary orbit. That means that the satellite's always overhead at the same time. That's how we get our TV and our cable. So those satellites, you have a big antenna on the ground, it just looks at the same place. That satellite doesn't move, it's just beaming the data down. It's great. But it's really far away, really far away. So it's 35,000 kilometers away. So you have to have a lot of power, huge panels like we saw. The lower orbits are nice, but they don't cover the same spot often. So they have these orbit tracks that sometimes can take 2 weeks to go over the same spot twice. So the more satellites that you have in orbit, like if you had a lot more of these little guys, the better you can cover the Earth. So these big ones they can see a lot of the Earth all at once, but they're so far away, they require a lot of power. And they can't see things up close, and they can't see a lot of changes that are small. But if you have a lot of them, you can increase that revisit rate. So just for fun, a couple other ways you can get CubeSats to space, and then I'll wrap. This is the first one that we sent to space. This is a satellite called Micrometeoroids on a orbital ATK on Antares rocket. And this is kind of a fun one. So this rocket went up to space station, and the satellites were on board as cargo. And they went to space station, and they were just basically put on the robotic arm at space station and ejected off, which I'll show a quick video of in a second. But the other way you can get off of space station is to have an astronaut throw you off. So this is a fun video to see if you haven't seen something like this before. So this is a cosmonaut, and there's a Peruvian CubeSat that he pulls out of his little satchel on one of his EVAs, extravehicular activities on space station. And he just kind of launches it. It's not a very common way to go, but every so often, people manage to pull that off. Bye. More often, you get sent up as cargo, and then you get ejected from the robot arm like this. So this one right there is our first satellite, Micrometeoroids, getting ejected. The other nice thing about being ejected from station instead of from a rocket is that the astronauts are actually there to take pictures. Woo! The rocket images are not very good, but these are great images to have. Okay. And this is kind of the last you see of it before you start getting radio communications from the ground, if you're lucky, with one of those big dishes or antennas that you have to set up. All right, so CubeSats check all the list of things that help us learn about space. So they really do. They're great training tools for big space exploration missions, and now they're even big missions just of themselves, constellations of them doing Earth sensing. So anyway, just to summarize, space exploration really lets us learn more about the Earth, the solar system, our galaxy, and our role in the universe by getting out there. Space is hard. How many people would agree that I've convinced you space is hard? Yeah? We need to do some work to make it happen. We can use tethered balloons, we can use weather balloons, we can use CubeSats to help learn about all those things, check all the boxes, and make sure we understand how to overcome hard. And we can use CubeSats for free rides to space for student and research projects. The other thing that I really want to the one other thing that I really want to convey before I go about the space business is it can be mythical. It can be like chasing rainbows and unicorns or chasing dragons or mythical creatures. Nothing really happens when you want it to. Everything's always late. Usually it's delayed for some reason. Things break a lot. Things don't work as planned. And it really takes people with mental toughness and a lot of positivity to be able to go back and do that again and again and again until you get it right. And to deal with the fact that 95% of the time you are just working your butt off. You're learning all the hard things. You're doing all the hard math. You're testing all the hard tests. And then 5% of the time, it is awesome. Okay. So you have to be a little nuts to be able to make it in that industry. And it's for the right kind of people. And I hope some of you guys I'll see you there and as the years go by, because it's a small community. So we all get to run into each other eventually. So I'm happy to take questions and hope you guys have a great lunch. Yep, so you're right that having a lot of satellites in space can create a lot of radio frequency interference and noise. For the most part, they try to give licenses in very limited bands to help with that, and it's really controlled. Some of that stack of paperwork is just figuring out and coordinating what radio frequencies you can use. But yeah. Internet over balloons? I think it's a great idea, and there are probably regions where it makes sense. I will say that balloons are hard, and they're really unpredictable. So you're trading those two things. It's still hard. You have a little bit more access to it. They go up and come down. So maybe there's some recovery of cost there. Yeah.
So when you're layering a material with so many chemicals and everything to prevent certain side effects, is there any possibility that they can react with one another and cause some side effects?
It's possible. You try not to have that happen. So when you're treating all of the surfaces to make sure that that there's no corrosion, for example, or when you're using like insulating, there's like Mylar and Kapton. That's the shiny gold stuff that you'll see for insulation, just like thermoses insulate. One of the side effects of that is it's conductive, so you don't want it touching things because it'll short. And the other thing is sometimes you'll use some of these coatings and blankets and you'll forget that they have structural properties too. So when things get cold and hot, they'll pull things apart and together, and there's a lot of interesting things. But for the most part, a lot of the paints and the coatings they try to make them pretty passive so they don't interact. Okay?
Okay, one on the far end here, and then we'll start to make a few lunch announcements. Go ahead.
Do you think it would be possible to get a CubeSat onto like a comet and send it out into space?
Do I think it's possible for a CubeSat to get near a comet? I think if you have a propulsion system for CubeSats that's effective enough, it may be possible. I don't know of any right now that that are capable enough to do that, but you could maybe stage it so you have a spacecraft that gets it out there and then deploys it. Something like that.
All right, so actually, Kerri, we have a T-shirt we'd like to present to you.
Okay.
And, we have an extra one for your assistant. So
Oh, thank you, thank you. Thanks, guys. Hey, I like beavers.